My name's Tim Hanna. You'll notice on my ID it's got some letters and numbers after that. That's my amateur radio call sign, WB9NJS. I've had that call sign since I was in high school, and I'll let you know, folks, that's been a few years. We have several others who are part of this endeavor, other instructors, one of which you'll hear from this evening. The first of which you'll hear from this evening is Michael Carroll, KM6OTE in Fort Bragg. Other instructors include Steve, KJ6EIF in the Ukiah area, actually up in the hills west of Ukiah. And Mike Carter, KC6MGM. Mike will also be giving he'll be doing the final presentation on all of the rules and regs. So you'll get to hear from all of us at one point or another. There's other folks who are key to this as well. Nick and Dan and others who help us manage this whole thing. So that's who's part of this show. I do want to apologize for those of you who were hoping to have in-class instruction tonight face-to-face. Just didn't work out that way with the weather forecasts and variability, so we opted for Zoom only tonight. If conditions improve and interest is there, we'll see what we can do about instituting in-person options for next week, but that's to be determined at this point. So how this whole thing is organized, we have 5 consecutive Tuesday evenings with about 2 hours set aside each evening. Each night we will cover anywhere between 1 to 3 of the 10 segments of information that are included in the exam. Most of the nights it'll just be 2. We typically try to set it up so we have a different presenter for the second half, so you don't have to listen to the same person drone on for 2 hours. We'll go ahead and move forward with the presentation. First of all, I do want to thank everybody who's making this possible. The presentations are sponsored by several organizations. Mendocino Auxiliary Communication Service, MAX, that's an arm of the Office of Emergency Services. Mendocino County Amateur Radio Communication Service, McCarks, is an informal, semi-formal, informal club that supports emergency communications activities and training in the county. Willits Amateur Radio Society, WARS, is a general interest ham radio club, many members throughout the county and beyond. They are an active club that does a number of events and usually with monthly get-togethers. Adventist Health, the folks at Ukiah Valley and Mendocino Coast have offered to make space available among other resources, even though we're not using that this evening. Mendocino Public Health, Mendocino County Public Health, again, a sponsor who's helping make this possible. If things go to plan, next Tuesday's session in Ukiah will be actually at Public Health rather than at Adventist Health. And Log Valley Health Center, our friends up in Laytonville, giving us a North County, Central County presence. Those are the folks who make it possible. Again, thanks to all. So here are the details on the exam. There's 35 multiple choice questions. Every single one of those questions is published in a publicly available database, questions and answers. So there should be no surprises on the test. Trying to memorize all 412, I think it is, or so questions that are in the pool is a bit tedious. So we really think it's best for you to learn the information that leads you to the right answer, develop the understanding. One thing you might notice, okay, so pretty much 2 presentations per night, with a few exceptions. They'll be hopefully about 40 minutes in length. We'll take a break, we'll come back. There'll be time for questions and clarifications. Let me do this. So this is how the sessions are organized. Tonight we are going to cover Electrical principles and electronic components, that's sections T5 and T6. 4 questions in the pool from each of those groups. Next week, we're going to go into safety and practical circuits. That is, let's see, T0 for the safety. And whoops, sorry about that, folks. T0 for safety and T7 for practical circuits. Week 3 is the week we'll cover 3 segments. Radio wave propagation, T3, T8, signals and emissions, and T9, antennas and feed lines, getting into some of the more technical nitty-gritty of it. The 4th week, move on to operating procedures and general amateur radio practices. What do you do? How do you actually do things when you get on the air? And week 5 will be devoted to the FCC rules and regulations. Please note that 6 of the questions of the 35 come from rules and regulations. So there's a real interest to make sure you know the rules that you're playing by. As I mentioned, there are other study materials that are available that you can access through our website, the McCark's website. There's also others that will be listed to you. A lot of online resources for taking practice tests. This session is being recorded so it can be viewed at a later date on YouTube. So the notes are available, presentations are available, videos will be available, and the presenters will be available too. I believe Mike emailed everyone earlier with a list of the names and email addresses of the people who are presenting. So if you run across a question later and want to get clarification, you can contact the presenter. As I mentioned, if you have a question during the presentation, if you can use the chat to post it, we'll come around and pick up questions when we gather a few. If you do have chosen to use a printed study guide, the one that at least I reference and the one that I recommend is the Gordon West. That's the yellow book, and make sure that it's the 2022 to 2026 version of that. The questions in the pool change every 4 years, some a little bit, some a lot. So the current one is that 22 to 26. So in tonight's lesson on electrical principles, talk about the following basic electrical principles, concepts and definitions of the units of measure, Ohm's law, how to do power calculations, and a quick view on basic electrical components. Now, Michael will get into that in greater detail in T6 after I complete mine. And the last section is unit, prefix, multipliers, and how to convert between those. So a lot to cover in this area tonight. Our discussion of electronics will begin with something that's really very basic, and that is the electron. Atomic theory is defined by chemists and physicists, say that all matter is composed of atoms. These atoms consist of a dense nucleus surrounded by a cloud of orbiting electrons. In some materials, these materials are held very tightly. In other cases, those outer electrons are not. So if there are a lot of free or loosely held electrons in the outer orbits, it's easy to move those electrons. And those materials like that are known as conductors. Metals are a good example of conductors because they have many free or loosely held electrons in their outer orbits. When those electrons are tightly held, the material is an insulator. Good example of insulator is glass, rubber, plastic. So we're talking about how electrons, what makes an electron move in an electrical circuit? Well, there has to be some kind of force or pressure, and that's known as voltage, also abbreviated as EMF for electromotive force. It's a force that makes electrons move in a circuit. It's the pressure. The basic unit of EMF or voltage is the volt. And by the way, tonight we're going to have a tour of Europe and even America in the late 18th to early 19th century. We'll be talking about a lot of scientists, including Volta, who the volt is named after. So the flow of electrons that occurs in an electrical circuit, the actual movement of them in response to that pressure or voltage is known as current or electrical current. The basic unit of current is the ampere. Oh, there's another old scientist, French this time. The letter used to indicate current in an equation is the letter I. So for voltage, it's E because it's electromotive force. For current, it's I. So not all conductors are equal. Some conductors are better than others. Good conductors, such as silver, gold, copper, require less voltage to achieve the same flow of current. That property that resists the flow of electrons in an electrical circuit is known as electrical resistance. That's what resists electron flow. And the basic unit of electrical resistance is the ohm. And there we go with the letter R used to abbreviate it in any equations and the equations that we'll be discussing. And the ohm, well, that's another. In this case, a German physicist and mathematician, Georg Simon Ohm, who was an early one working on electrical principles and properties. By the way, you don't have to memorize who these units are named for. I'm just throwing it in so you understand where those names come from. So, direct current, DC versus alternating current, or AC. Direct current flows only in one direction. Alternating current, or AC, alternates between positive and negative directions. That's the wording that's used on the test question. Alternating current alternates between positive and negative directions, where direct current flows in only one direction. So, the number of times per second that alternating current completes that cycle from neutral to positive to negative and back to neutral, the number of times per second that occurs is called the frequency of that alternating current. The unit for frequency is hertz, and guess what? That's another old scientist, a little bit closer in time frame to us, but Heinrich Hertz, a German physicist, who was first conclusively proved the existence of electromagnetic waves. So he got the frequency unit named in his honor. So frequency is the number of times per second that a complete cycle, positive to negative and back, is completed. So the opposition, we talked about opposition to electron flow in the DC circuit being resistance. There's something similar but slightly different in an alternating current circuit. The opposition to AC flow is known as impedance. Okay, and there's a lot more technical aspects of that we're not going to dive into now, but the opposition to AC flow is impedance. And guess what? The basic unit of impedance is also the ohm. So a little bit more about direct current. Batteries are the most commonly used supply for direct current, or DC. Most mobile amateur equipment does operate on DC. It's designed to operate off the DC power source in a vehicle. AC, alternating current, can be converted to DC in order to power that amateur equipment if you want to do it inside your house. And most mobile transceivers do typically operate on that 12-volt DC. So there's a little summary of DC. Not that many questions on the test this time about that. But let's talk about alternating current. That's what the commercial power grid supplies to homes and businesses. It's an alternating current operating at a frequency of 60 hertz, 60 cycles per second. Radio waves are also a form of alternating current. And radio frequency energy, which is abbreviated as capital RF, RF is a type of electromagnetic energy. And we'll delve into that a little more in future session. So, keep in mind, and this is one of the new questions, we talked about both impedance and resistance. They both oppose the flow. Resistance opposes the flow of all types of current, direct, alternating, or RF. That is one of the questions. But there is a formula that describes or defines that relationship between current, voltage, and resistance. That's known as Ohm's law. Here's another old-time scientist. I think we talked about him, didn't we? Georg Ohm. With a fixed resistance, the current will increase as the voltage increases. And if you think about that, if the voltage is the pressure that's moving those electrons along, if you increase the pressure without changing the degree of resistance, that flow will increase. Same as it would in a pipe. If you have a pipe of a fixed diameter and there's water flowing through it and you increase the pressure behind that, then the flow through that pipe will increase. So with fixed resistance, current increases as voltage increases. With a fixed voltage, the current decreases as the resistance increases. So let's go back to that scenario. You have a pipe connected to a tank of water with a fixed pressure behind it. If you go to a smaller pipe and increase that resistance, the flow or the current will decrease. So here are the equations that are used to describe, or these equations are different ways of expressing Ohm's law. So in this case, the voltage E equals the current multiplied by the resistance, and that follows along. If you look at that equation, if you increase the resistance, or if you increase the voltage, you'll get a higher flow. Okay, I'm getting off track here. All three forms of this equation may be included in one of the test questions. So in this case, current equals the voltage divided by the resistance. And somebody needs to mute. We got some feedback going on there. Okay, I think we're good. Okay, so three ways of expressing Ohm's law. Voltage equals current multiplied by resistance. Current equals voltage divided by resistance, or resistance equals the voltage divided by the current. Some simple algebra there, if you're up on your algebra. Okay, so there's a simple way, I think, of trying to remember this, and this is a little tool that you can sketch out and use. Some folks refer to this as the magic wheel for Ohm's law. To use this, you simply cover the unknown quantity and apply the formula. So let's have a look at this. So in the case where we have a resistance of 2 ohms and a current of 5 amps, well, you cover the E, you have I, 0.5 times the resistance 2, that gives you a value of 1 volt. So another example, If you have a voltage of 120 volts and a resistance of 80 ohms, what kind of current is going to flow through that circuit? Well, you cover the I and you have 120 over 80. Divide that out. Your answer is 1.5 amps. Third example, a voltage of 90 volts and a current of 3 amps. Again, you cover the unknown R and divide that out, and you'll have a 30 ohm resistance in that circuit where 90 volts produces 3 amps of current. Okay, we're going to talk about another old-timey scientist in this next section about power. And power is defined at the rate at which electrical energy is used. The basic unit of electrical power is the watt. You've probably heard that term. Now you know where it comes from. James Watt was a Scotsman who's known primarily for significant improvements in the steam engine, but we also give him credit for the electrical watt. I'm not sure why, but we do. So the very simple formula for determining the power in watts and in a circuit to determine the power that's being used, you multiply the voltage E by the current I to get the power in watts. So there's the formula. We can rearrange that as we did the other ones. The current equals the power in watts divided by the voltage. And again, we can use a simple tool, the pi tool. I like it because it'll look if you go clockwise from the top. Well, no, counterclockwise from the top. It spells pi. Power on the top, current in amps, and voltage on the bottom. The same deal. If you don't know the watts, you cover that out. And in this case, you have 13.8 volts, 10 amps. You multiply that out, 138 watts in that circuit. 12 volts, 2.5 amps. You don't know the watts. Well, that's the easy one. You multiply the power or the voltage by the current to get the power in watts. So 12 volts, 2.5 amps, that's 30 watts. Final form of the equation here, and these are all taken directly from the test. These values will appear in possibly one of the tests on one of the questions on your test. So 12 volts, 120 watts. We don't know the amps. We cover up I. We divide 120 watts by 12 volts, and we come up with a current of 10 amps in that circuit. So that's power. Changing power levels is another thing that proportion of the tests, and changes in power levels are expressed in decibels. Notice the capital B, that means it's part of a proper name. In this case, Alexander Graham Bell is where the decibel comes from. There's 4 possible questions regarding decibel calculation. We won't get into the math here. I'll just show you the basic format of it. A doubling of power, if you double the power, in this case from the question from 5 watts to 10 watts, that's a positive or a +3 decibel change. So doubling the power is a +3 change in decibels. If you halve the power, you cut the power in half, it's a -3 dB change. So the question on the test asks you about a 3 dB change. Well, that's a quartering of the power. You have the power the first time, in this case from 12 watts to 6 watts. That's a -3 dB. And if you have it again from 6 watts down to 3 watts, that's another -3 dB. You add those together and the net change is a -6 dB when you quarter the power. And the last question that might appear on the test is what a 10 times increase in power is from 20 watts to 200 watts. And that equals a 10 dB change, a +10 dB change. So if you 10 times the power is a 20 dB, or I'm sorry, is a 10 dB change from 20 watts to 200. Okay, take a little break here and we'll run through some of the questions on the test. So I will give you a second to look at that. What is the name for a flow of electrons in an electric circuit? Is it voltage, resistance, capacitance, or current? Well, it's current. That's the flow of electrons in an electric circuit is known as the current. That's measured in amps or amperes. Why are metals generally good conductors of electricity? Because they have relatively high density, they have many free protons, they have many free electrons, or all of these choices are correct. Well, in order to be a good conductor of electricity, it's the electrons that need to flow freely. So the correct answer is C. They have many free electrons. Okay, which of the following describes alternating current? A current that alternates between positive and negative directions, a current that alternates between a positive direction and zero, or a current that alternates between a negative direction and zero, or all of the above are correct. Well, no. Alternating current is defined as a current that alternates between positive and negative directions as far as which way the electrons are flowing. Electrical power is measured in which of the following units? Is it volts, ohms, watts, or amperes? Well, just think of old James Watt and his steam engine. Electrical power is measured in watts. What is the resistance of a circuit when 3 amps flow when connected to, I'm sorry, I got to move things around here on my screen. When connected to, that's better, connected to 90 volts, what would be the resistance that allows 3 amps to flow with a pressure of 90 volts behind it? Well, that means there's a 30 ohm resistance in that circuit. Okay. Move on to very, very basic components. As I mentioned, Mike will get into this later in the next section. A resistor is a type of component that is used to add electrical resistance in a circuit. Makes sense. Resistor adds resistance. These are some of the symbols that are used to represent that when you sketch out an electrical circuit. There'll be more on this later, but resistors may be variable, as an old-fashioned volume control was, or they may be a fixed resistor. Another component that we'll talk about now is a capacitor. And capacitors are devices that store energy in an electric field. So capacitors store energy in an electric field. They're metal plates or conductive metal surfaces that are separated by a thin layer of insulating material. The basic unit of capacitance in a capacitor is the farad. Oh, here we go. Another old scientist, Michael Faraday, who was an Englishman, contributed to the study of electromagnetism and electrochemistry. So we commemorate him with the unit of capacitance is the farad. And here are some symbols for both fixed, variable, and a polarized or electrolytic capacitor, the one that's got the little plus sign by it. Those are symbols for capacitors. Those are devices that store energy in an electric field. So what do these things look like? Here's some pictures of resistors. They're usually, but not always, tubular. They usually have stripes, colored stripes on them that indicate the value of the resistance. The larger the resistor is, the more power it can dissipate in watts. So in this picture, the little resistor on the right-hand side is probably capable of handling about 1/8 of a watt, where the one, the big fat one on the left-hand side is probably several watts, 3 to 5 watts, I would guess. That's what resistors look like. This is a variety of capacitors that you might encounter. Quite often, tubular, the ones that are, the big tubular ones are types of electrolytic or polarized capacitors. You'll notice some that are on the right-hand side of the screen that have little half circular plates. Those are a type of a variable capacitor. What you're seeing there are the conductive surfaces, and in this case, they're separated by air. And as you rotate the knob, those plates engage and disengage and change the capacitance. But that's what capacitors look like. They store energy in an electric field. But there's another way to store electric energy. And that is what inductors do. Inductors, however, store energy in a magnetic field. Capacitors, electric field. Inductors, magnetic field. What's an inductor? It's basically, in its simplest form, a coiled wire. There may be nothing in the center of the core. There might be some kind of ferrous material to enhance the magnetic field that it generates. Inductors store energy in a magnetic field. They're coiled wire. The basic unit is the Henry. Oh my gosh, Joseph Henry, an American scientist this time. So again, basic unit of inductance is a Henry. These are common symbols for an inductor. Kind of looks like a coil of wire. The one in the center with the bars indicate that there's some kind of ferrous core. The one with the arrow through it indicates that it's a variable inductor. What do they look like? Here's pictures of them. They come in all kinds of shapes and sizes. The one furthest left is a very simple inductor. It's an air core inductor. The one next to it has been wound on a donut or toroidal core of ferrous material. And the picture at right shows various forms of fixed and variable inductors. Okay, so let's talk about how you can hook up these components in a circuit. Components might be connected in what's called series, or end to end, or they may be connected in parallel, where the components are wired in side by side. The example on the left shows two resistors in series. The picture on the right depicts two resistors connected in parallel. So, what do you need to know about series circuits for the test? Well, in a series circuit, the components are connected end to end, and the same DC current flows through all of the components. So what goes in one end comes out the other as far as the number of electrons flowing through it. Parallel circuits, well, those components are connected side by side, and in parallel circuits, the same voltage appears across all of the components. That's the key to the question. That the same voltage appears across all components in a parallel circuit. Okay, time for some more questions. What describes the ability to store energy in a magnetic field? Well, we just talked about that. We know it's not resistance. We haven't talked about admittance. Capacitance is an electric field, so the correct answer for storing energy in a magnetic field, that is inductance, and the basic unit of inductance is the Henry. What's the unit of frequency? Oh, well, we've got different names here to choose from. Hertz, Henry, Farad, or Tesla. Well, frequency, which is the rate at which an alternating current completes a cycle, the number of complete cycles in a second, and that's named in honor of Heinrich Hertz. So basic unit of frequency is the Hertz. Basic unit of capacitance. Okay, Farad, ohm, volt, or Henry. Capacitance, the ability to store energy in an electric field, is the Farad for Michael Faraday. And how much power is delivered by a voltage of 13.8 volts and a current of 10 amperes? Well, to calculate power, it's voltage times current. So that gives us an answer of 138 watts. Which type of circuit is the voltage the same across all components? Well, we haven't talked about resonant or branch, so that narrows it down to series or parallel. But in a parallel circuit, the same voltage appears across all components. And for some reason, I just duplicated that one. In which circuit is a DC current? Oh, I'm sorry. No, I did not. In which type of circuit is the DC current the same through all components? In which case is the current the same? Well, again, resonant and branch drop out right away, so it's got to either be series or parallel. And if the DC current is the same, that means it is a series circuit. Okay, we're getting down to the home stretch here, which is good because we'll want to take a break and see if we have any questions to address. So we talked about basic unit. In some cases, the actual value or component or the unit of measure might be several times greater or only a small fraction of the base unit. For example, capacitance. You are unlikely to see a 1 farad capacitor. You'll mostly see capacitors that are in the microfarad or also known as the picofarad range. So there are different multipliers used. An example, frequencies, actually amateur radio frequencies are often in the millions of hertz, thousands or millions of hertz. Capacitance, yep, maybe a millionth of a farad or even a billionth of a farad. Unit multipliers are used to simplify that measurement and the conversion, hopefully. And here are the prefixes and their multipliers that you're likely to encounter. The pico is 1/trillionth of the base unit, and that's usually in terms of a capacitor. You'll find a picofarad capacitor. Micro is 1/millionth, that's 10 to the minus 6. Pico is 10 to the minus 12. Milli, or 1,000th, is 10 to the minus 3rd. Now we'll go on the other side. Kilo, that's 1,000. So 10 to the 3rd is 1,000. Mega, million, 10 to the 6th. And giga, or billion, is 10 to the 9th. And all of those prefixes you'll run across in various units in amateur radio. So how do you deal with these conversions? How do you convert from one to the other? Well, here we'll give you an example. 1,000 hertz is the same as 1.0 kilohertz. Notice the abbreviation is a small k followed by a capital H and then a Z. It's a proper name, so hertz is capitalized. So kilo, small k, hertz for 1,000 hertz or 1 kilohertz. 1 million hertz is equal to 1,000 kilohertz, which is also equal to 1 megahertz. Notice in this case, the M is capitalized. And you may go, well, why is that? Well, that's to distinguish it from the milli prefix, which is 1,000. So a small, and you'll often see that in amps or volts. You'll see a small m and a capital V for a millivolt. But if it's mega, it is the uppercase. Again, that's from one of the questions. Proper abbreviation for megahertz is capital M, capital H is small z. 1 volt, well, that's the same as 1,000 millivolts, which is also the same as 1,000,000 microvolts. 1 microfarad, well, that's the same as 1,000,000 picofarad. So how do you keep all of these straight? Well, you can do it by doing by working with the exponents in the unit multipliers to determine where you move the decimal. So if the difference between the exponents is positive, you'll be moving the decimal point to the right. If the difference in exponents is negative, the decimal point will move to the left. So here's some examples. To convert 3.525 megahertz, which is 10 to the 6, to kilohertz, you'll take the multipliers, 6 and 3, subtract them, and that gives you a result of positive 3. So the decimal will move 3 places to the right, and that gives you an answer of 3525 kilohertz. That's what equals 3.525 megahertz. All you have to do is subtract the multipliers in the exponents. Here's another one. How do you convert 500 milliwatts, which would be 10 to the minus third, to watts, which is 10 to the 0? That's not supposed to be 100. That's supposed to be 10 to the 0. So minus 3 minus 0 gives you an answer of minus 3. So the decimal will move left 3 places because it's minus. So you'll move that decimal from 500 and 3 places to the left. It gives you 0.5 or 1/2 of a watt. Okay, so here are all of the ones that are in the question pool. I suggest you learn to manipulate the exponents, but if you want to just memorize them, here it is. 1.5 amps equals 1,500 milliamps. 1,500,000 hertz is the same as 115 or 1,500 kilohertz or 1,500 kilohertz. 1 kilovolt is the same as 1,000 volts. 1 microvolt is 1 millionth of a volt. 500 milliwatts is equal to half a watt. And 300 milliamps, thousandths of an amp, 3,000 thousandths of an amp is equal to 3 amps. 3.525 megahertz is the same as 3.525 kilohertz. And 1 million picofarads equals a microfarad. 28,400 kilohertz is the same as 2.4 megahertz. And finally, 2.525 megahertz is the same as 2.425 gigahertz, which happens to be an amateur band and also a Wi-Fi band, 2 gig Wi-Fi band. So those are the units and multiplier conversions that will appear on the test. Any of those might appear on one of the 4 questions from this segment. Okay, we'll wrap it up with a couple quick questions from the pool, and then we're ready to go to break. So which equals 1 microvolt? Well, micro is a millionth, so it's not a million volts. That would be a megavolt, not a thousandth. It's not 1,000 kilovolts. It's a fraction of a volt. So the correct answer is D. 1 millionth of a volt is what 1 microvolt equals, which is equal to 3,000 milliamps. Milliamps is 1,000th of an amp, so 3,000 times 1,000 gives you an answer of D, 3 amperes, which is equal to 3.525 megahertz. Well, we've just gone by that one twice. You're going to move the decimal 3 places to the right and get an answer of 3.525 kilohertz.
So this is section T6, and it will be to some extent a little bit of repetition of what Tim just did, but we're going to look at things like circuit diagrams and some of the functions of the components, and we'll go over some of the questions. Now, one of the things, Tim did a great job of going over lots of stuff, and even though there are only 4 questions in T5 and 4 questions in T6, things like Ohm's law, the power calculation, and the units are going to be used over and over again in all the sections. So if no matter what, you have to study the Ohm's, really know cold Ohm's law, the power calculation, and how to convert units, megahertz, and so on. So, and in terms of the, let's see, how do I do this? In terms of the preparation for the test, I didn't get my license as long ago as Tim. I got mine about 5 years ago. I've got all 3 licenses. And I found that there were some really useful things to help me prepare for the test. The first was that the question pool, ARRL, the ham radio, the National Ham Radio Association, has all of the questions and answers on their website. And it's a little hard to give you the link for that, but if you drill down, you can find it, or if you can't find it, email me and I'll send you a copy. But it helps to have that question pool. Those questions are also in the study guide that they recommended, the Gordon West study guide. Also, I found that there is an app, a free app called hamstudy.org that's fabulous. It's like flashcards that give you a test question. You give it an answer, and if you get it wrong, it'll tell you what the right answer is, and it'll record that you need more work on that section, and it'll give you data on how you're doing and tell you when you're getting the level of answers to the level of answers that will let you pass the test. So I really encourage you to get the hamstudy.org app. It'll run on your iPhone or your computer or your pad. And the third thing is that there's an alternative study guide. The Gordon West book is really good and it's not very expensive, but the ARRL puts out one that's more expensive and more detailed. And it's actually a good reference book even after you pass your test. It makes sure, like Tim said, you got to get the latest edition, the 5th edition in this case. It's a little bit more expensive, but I really recommend it if you want a more technically detailed study guide. So we need to look at, in this section, we need to look at the components and how they're used. We need to, you need to be able to identify components in wiring diagrams. So they'll give you a schematic and you have to say, okay, well, that's a transistor or that's a diode. And we'll look at the component functions. Tim has done some of that, but we'll review that. And we'll try to go over some of the questions. So here's an easy one. The batteries, we all are used to using batteries. One of they will ask you about chargeable versus rechargeable, and the carbon batteries are not rechargeable. The lead acid, NiCad, nickel metal hydride, and lithium ion are all chargeable. These are the schematic symbols for batteries. So here's one of the questions. Which of the following chemistries is rechargeable? And so here's a trick about the test is that it's almost always true that one or two of the answers are obviously not right. And so in this case, we know that lithium ion is rechargeable because that's what's in our computers. We know that lead acid is rechargeable because that's what's in our cars. So at least 2 of these are right. So that is likely the case that all 4 are right. So D is the right answer. Which of the following chemistries is not rechargeable? So we know that lead acid is not rechargeable. We know is rechargeable. We know that lithium ion is rechargeable. We know that NiCad is rechargeable. So the answer is B, carbon zinc. So switches, this seems very simple, but there are several test questions on this. So a switch is used to connect and disconnect electrical circuits. And they talk about poles and throws. So if you have just a simple switch that's an on-off switch, you have one pole, that's this, and one throw. In other words, it's either on or off. So that's a single pole, single throw, or designated SPST. A single pole double throw is where you switch from one circuit to another circuit. And so this is a single pole double throw. And then you could have a double pole double throw. So you have 2 poles and each of them can go to each of 2 different positions. That's called a double pole double throw. So what is the function of a single pole double throw switch? So single pole double throw, that's this circuit. So it looks like you can choose whether you want to connect to this circuit or this circuit. So the function of a single pole double throw is not a single circuit open or closed. It's not 2 circuits open or closed. It's not 2 circuits switched between one or the other of 2 circuits. It's a single circuit switched between one or 2 circuits. So the answer is C. So a relay is just an electrically controlled switch. Okay, we've got to admit somebody here. There we go. All right. A relay is an electrically controlled switch. So it follows the same rules as a switch, but it has this extra coil, and the coil is magnetic. And so when you energize this coil, it pulls it it's in the normally closed position. When you energize the coil, it goes to the normally open position. And the contacts are normally are labeled NC and NO. And common is this unit here. So the designator on a schematic is usually a K or sometimes an RLY. So here's the test question. What is a relay? Is it an electrically controlled switch? Is it a current controlled amplifier? Is it an inverting amplifier? Is it a pass transistor? Well, three of these don't make any sense. So A is the electrically controlled switch. A is the right answer. Okay, fuses. Everybody's had fuses blow from one time or another. Fuses are to protect your circuit. It's really important that you that all of your ham radio gear be fused, because you don't want to burn out your equipment. That would be a very expensive mistake. So fuses are typically designated by the amount of current, and they on a schematic they look like either a box or this squiggly line, or you could have a circuit breaker that has this this push button. You've really got to make sure that you have the right rating of a fuse. So what is the electrical component? Another test question. What is the electrical component used to protect other circuit components from circuit overloads? Is it a fuse, a thyratron, a varactor, or all of these choices? Well, we haven't talked about a thyratron or a varactor, and I don't think we're going to. So it's not all of these choices, so it must be A, the fuse. Indicators and displays. We can have analog meters. We can have digital meters. We can have LEDs. LEDs now come in lots of different colors. And the symbol is a circle with a letter in the middle. In this case, that's an amp meter, but it could be volts. It could be anything. It could be power. So this is the symbol for a meter. And resistor. Tim talked about resistors, so I'm just going to repeat this. A resistor's function is to oppose the flow of direct current. And there are a couple kinds of resistors. Tim showed you a whole variety. The symbol is the squiggly line, but you could also have a variable resistor which has three leads. There are the two resistor leads and the variable lead, and it's a variable resistor. It's also called a potentiometer or a pot. It's often called a pot. It's used for changing voltage for it could be used on a volume control. Lots of different. You're going to see lots of those. Capacitor. Tim talked about that. Capacitor is to store energy in an electrical field. Now, here's a trick to the questions: is that if they say store energy in an electrical field, it's always a capacitor. If they say store energy in a magnetic field, it's always an inductor. And those are the words they use. You could argue that maybe that's not perfectly correct in electrical engineering terms, but that's the terms they use in the test. And so stores energy in an electrical field, that's a capacitor. Now, a capacitor is made up of two conductors with some kind of dielectric, a non-conductive surface in between. And it turns out that the bigger the surface area, the higher the capacitance. The smaller the distance between these two, the higher the capacitance. And so Tim showed you a whole bunch of different kinds. They range from a couple of you can actually get a 1 farad capacitor these days down to picofarads, and they come in all different sizes and voltage ratings. The thing about capacitors, and this will help you when we start talking about resonance, the thing about capacitors is they are an open circuit for DC. A capacitor is an open circuit for DC, and the higher the frequency, the lower the reactance, the resistance to flow of current across the capacitor. We'll talk more about that in a minute. This is a variable capacitor. Tim showed you a couple of types of variable capacitors. This is often used for tuning circuits. And as Tim pointed out, they're measured in farads. This is an inductor. An inductor is shown as a coil, could be a variable inductor, also a variable inductor, and it could have a let's see, can I get rid of this? It could have a core. It could be an air core or it could be an iron core. And so this is the terminology that the test uses. It stores energy in a magnetic field. So if we ask you a question, what component stores energy in a magnetic field? It's an inductor. Here's the trick about inductors is at DC, an inductor is just a wire. So there's no reactance to an inductor at DC. And the higher the frequency, the more reactance there is in an inductor. So if you just remember that a capacitor is an open circuit at DC, an inductor is a short circuit at DC, that'll help later on when we're trying to look at the frequency effects. So when you put two inductors together with a core, that's called a transformer, and they typically use a transformer to change the voltage. So the input voltage might be the 110 volt AC that comes out of your excuse me, that comes out of your wall, and you might get 12 volts AC out. And so the ratio of the turns is what determines what the voltage change is. And so they share a magnetic field. There's no energy created or destroyed here. Wait, let's go back. All they're doing is changing from higher voltage to a lower voltage, or a lower voltage to a higher voltage with the same power, roughly the same power. There's some losses, and if this is 110 volts and this is 12 volts, the 110 volts is going to draw less current than the 12 volts. 12 volts will have more current. So the ratio of the voltage to the current will change. So we talk about shielded wire, and in ham radio, you see a lot of shielded wire. We're not going to go into much depth, but the function of shielded wire is because as the frequency goes up, the signals want to disperse. They want to broadcast, and so the shielding prevents unwanted signals from getting into your signal wires, and also your signal wires from interfering with other things that might be going on. So we'll talk more about shielded wire. This is a diode, and a diode. There are lots of different kinds of diodes. Diode only allows current to flow in one direction. So this is the positive side. This is the negative side. It can flow this way. Electrons flow this way. But the cathode, this is a question on the test. The cathode is always marked with a stripe. So this bar, if you looked at a diode, it would have this stripe. So here's a diode with the stripe. Here's a diode with the stripe. So that's how you tell what the polarity of the diode is. And these are the schematic symbols. This is a regular diode. There are various other kinds of diodes. There's Zener diodes and Schottky diodes and tunnel diodes, varactor diodes. We don't have to get into that, but there will be different symbols for those. This is a little video that shows what happens with it. I mean, this is an old style rectifier, a vacuum tube rectifier, but it works the same as a diode. Is that the voltage goes positive and the voltage goes negative, but it only goes one way through the rectifier. So you get, rather than AC, you get a pulsating DC out of the diode. Also, this is the symbol for a light emitting diode, or an LED. Okay, so and the current direction to make the LED light is in this direction. The LEDs are used for displays and as individual lights. Okay, transistors. You'll see a lot of transistors. There are two basic types of transistors. There's a junction transistor and a field effect transistor. These are the symbols. This is the junction transistor. This is the field effect transistor. schematics. They're usually called Q. Q is the symbol for both types of transistor. So the bipolar junction transistor is typically used as an amplifier, and the way it works is that a small amount of current flows from the base, this point right here, to the emitter, and then a larger amount of current flows from the collector to the emitter, and they're proportional. So the more where'd it go? So the more signal you have on the base, the more current you have from the collector to the emitter, and that's how it can be used either as an amplifier or a switch. It's called a bipolar junction transistor, or a BJT. Let me go back, and this is called the base. This is called the collector. This is called the emitter. Okay. So here's an example of how a transistor will amplify a signal. If you have a small signal here, and it's coupled with a capacitor. Remember, we said capacitors have a lower impedance as the frequency goes up. So this is an AC signal. So the capacitor couples, and it will create a voltage on the base, and that will determine how much current flows from VCC through the transistor and through the base, and the signal will be out here. So if this voltage goes up, the current goes up, and the more current is dropped, the more voltage is dropped across this resistor, and so the voltage goes down. And so what we have is an amplifier. We have a small signal here. We have a large signal here that's 180 degrees out of phase. But this is a basic amplifier circuit. You'll see this a lot. Okay. So an integrated circuit is they're also called a chip, but an integrated circuit has lots of semiconductors. It'll have diodes and transistors and all kinds of other stuff in one device. And these could have 72. They could have 100 different pins. They could have amplifiers. They could have transistors. They can have regulators. They've got all kinds of things. So an integrated circuit combines several semiconductors and other components into one device. This is the schematic symbol, and like I said, you could have lots of pins out here, and they'll each be designated, and there'll be some key to what's what. Now this is the symbol for a special kind of integrated circuit that's called an operational amplifier, and this is a discrete amplifier that has all the components in it to do amplification. You have to add some resistors around the outside, but this is called an operational amplifier. Okay, so this is the kind of thing that will happen in your test. You'll be shown a schematic like this, and you'll have to identify the components. And so I'll just go through these. So number 2, that's a fuse. Number 3, that's a single pole, single throw switch. Number 4 is a transformer. Number 5 is a diode. Number 6 is a capacitor. Number 7 is a resistor. Number 8 is I didn't mean to do that. Number 8 is a light emitting diode. Number 9 is a variable resistor. And number 10 is a Zener diode, which is a regulating diode. And then this symbol here at the bottom, little fork thing, that's ground, or that's the common. So on the circuit board, this point and this point and this point and this point are all connected together. So this is an example of a schematic, and you'll be asked to identify the components in the schematic. So what type of component, what is component 3 in figure 2? So component 3 is a single pole, single throw switch, right? So single pole, single throw. So what is component number 1? That's a resistor. Component number 2 is a transistor. Component number 3 is an LED. Component number 4 is a battery. In this circuit, component number 6 is a capacitor. Component number 8, I can't see it. Oh, is a light emitting diode. Component number 9 think it's a resistor. And what type of switch is number 3 is a single pole, single throw. Everybody with me? Okay, so reactance is the equivalent of resistance only for capacitors and inductors. Okay, so like I said, as at DC, a capacitor is an open circuit, but and so it has infinite resistance, or the equivalent of infinite resistance, because it's an open circuit. But as frequency increases, the more of the signal gets pushed through the capacitor, and so the reactance goes down as the frequency goes up. That's called the capacitive reactance. An inductor is just a piece of wire at DC, but the higher the frequency, the higher the reactance. And so as the frequency goes up, the X sub C goes down from infinite down to some lower number, and the inductive reactance goes up. And this is important because we're going to talk about something called resonance. So, but impedance is the combination of the resistance plus the reactance, and the symbol for impedance is Z. And throughout all of ham radio, you'll be talking about impedance and impedance matching, and knowing about impedance, you'll need to know about this, okay? So here's why X sub C and X sub L are important, because the one of the most important principles in ham radio is resonant circuits. And resonant circuits are the frequency when the capacitor and inductors are at their minimum. In other words, as the frequency goes up, the capacitor is getting less and less reactance, and the inductor is getting more and more reactance. And so the frequency at which they are matched is called the resonant frequency, and we'll talk more about that later. But it's important that you understand what resonance is and how it affects. How it's based on reactance of the capacitor and the inductor. Okay, so antennas. There's a whole section on antennas. You'll get lots of information about antennas. The only point of antennas here is this is the symbol for an antenna. This is one of the symbols for a ground. Okay. And this is a certain kind of antenna. This is a ground in the ground. This is a ground rod with a big wire attached to it. So what is component 3? That's a variable inductor. What is component 4? That's an antenna. Somehow I lost my numbers here, but component 2 is a variable capacitor. This component is also a variable capacitor. So what is the electrical component that opposes the flow of current in a DC circuit? Okay, so the key here is DC. Anything that inductors are for AC, transformers are for AC, so you can eliminate those two right away. Inverters we haven't talked about, so it must be a resistor. The answer is B. What type of component is often used to adjust volume control? Okay, well, so it's not a transformer, because that's not adjustable. It's not a power resistor, because that's not adjustable. It's not a fixed resistor, because that's not adjustable. So it must be a potentiometer. The answer is C. Potentiometer, also called a pot. What electrical parameter is controlled by a potentiometer? We just looked at that, but it could be inductance, resistance, capacitance, or field strength. Well, we haven't talked about field strength, so that isn't going to be it. And so it's got to be resistance. B. What component stores energy in an electric field? Okay, remember I talked about this. Is the key term is electric field. So whenever you see what component stores energy in an electric field, it's always the capacitor. Always the capacitor. And again, you can eliminate varistor, because we haven't talked about that. And diode doesn't store anything. So the only choices are the inductor, the capacitor. And because it's the electrical field, electric field that we're storing, it's the capacitor B. What type of electrical component consists of conductive surfaces separated by an insulator? Well, it's not an oscillator. We know that. It's not a potentiometer. We know what that is. It's not a resistor, so it must be a capacitor. D. D is the answer. What type of component stores energy in a magnetic field? Now, again, this is the key term, magnetic field. Anytime you see magnetic field, we're talking about inductor. And again, we can do process of elimination. We're not talking about varistors. That's a semiconductor. Diode is a semiconductor. And so it's either inductor or capacitor, and magnetic field is an inductor. Okay, C. What electrical component is typically constructed with a coil of wire? So there's no coil of wire in a switch. There's no coil of wire in a diode. You can eliminate those two. And if you just look at the schematic symbol, that just looks like a coil of wire. It's the inductor, D. What is true about the forward voltage drop in a diode? So this one's a little tricky. It's a little lower in some diode types than others. It's proportional to the peak inverse voltage. It indicates the diode is defective, and it has no impact on the voltage delivered. This, you just have to memorize it, but the voltage is lower in some diodes than others. It depends on the semiconductor type, but the answer is A. And this is an example of, you can read all about it in the various review books, but just memorize the fact that different diodes have different forward voltages. What electronic component allows current to flow in only one direction? Well, we know resistors can flow in both directions. Fuses can flow in both directions. A driven element we haven't talked about, so it must be a diode, C. Which of these components can be used as an electronic switch? Well, potentiometer isn't a switch. A varistor isn't a switch. Thermistor isn't a switch, so it's a transistor. A transistor can be used as a switch. In fact, that's all of digital electronics is based on transistor switches. Which of the following components can consist of 3 regions of semiconductor material? So it's not an alternator. It's not a triode, because a triode is a vacuum tube, not a semiconductor. I'm not sure what a pentagrid converter is, but the answer is a transistor. A transistor is a 3-element. It's a BJT, a bias junction transistor, is a 3-element semiconductor that we looked at. What type of transistor has a gate, a drain, and a source? Okay, and we just looked at bipolar junction transistor. That's not right. We don't know what Tesla effect and we don't know what Tesla effect is. Varistor is not it. It's a field effect transistor. So the answer is B. A field effect transistor has a gate, drain, and source. How is the cathode lead? Oops, sorry. How is the cathode lead of a semiconductor diode marked on the package? With the word cathode, with a stripe, with the letter C, with the letter K. This is on the device itself. It's a stripe, B. What causes a light emitting diode to emit current? And that's the forward current. Again, there are 2 here that are obviously wrong. The capacitively coupled RF signal and the inductively coupled RF signal make no sense. So it's either one of these 2, and it's A. So what does the abbreviation FET stand for? And we just talked about that. It's not a frequency emission transmitter. I don't know what that is. It's not a fast electron transistor. I don't know what that is. A free electron transmitter. I don't know what that is. Field effect transistor is the right answer. D is an FET, and it's often called a FET. FET, field effect transistor. What are the names for the electrodes of a diode? And it's this one's a little tricky, but just memorize that it's C, anode and cathode. Which of the following can provide power gain? This one's a little bit tricky because a transformer changes the level of the voltage, but it doesn't change the power. And resistor dissipates power. We haven't. It's probably not a reactor, so B, transistor, is the right answer. What term what is the term that describes the device's ability to amplify a signal? It's not on resistance, it's not forward voltage drop, it's not forward resistance, it's gain, gain. And we saw the schematic of an amplifier. That's how a transistor works for gain. What are the names of the electrodes on a bias junction transistor? And that's B, emitter, base, and collector. And you just have to memorize that. Just look at the schematic, and it'll have an E, B, and a C on it. And if you know the symbol for a bipolar junction transistor, it'll have an E, B, and C. And so that's the key to the answer here. What is the name of an electrical wiring diagram that uses standard component symbols? Well, it's not a bill of materials. It's not a connection pinout. It's not a flow chart. It's a schematic. C, schematic. Which of the following accurately represents an electrical schematic? So wire lengths, physical appearance of the components, component connections, all of these choices are correct. Well, wire length is not on the schematic. So we know that wire length is not correct, and D, all of these is not correct. The symbols have some resemblance to the components, but they don't have the physical appearance. So it's got to be C, the connection of the components, C, component connections. Which of the following devices or circuits change alternating current into a varying direct current signal? A transformer changes the voltage level, but it doesn't change AC to DC. An amplifier, you can get gain. A reflector, I don't know what that is. So it's a rectifier. That's a diode or a rectifier, is how you change alternating current to a pulsating DC current, B. Which of the following reasons to use shielded wire? To decrease the DC power connection, to increase the current capability of the wire, to prevent coupling of unwanted signals, or to couple the wire to other signals. So the shield is just a conductor, but it goes around the other conductors. So it doesn't decrease and it's not used for DC power. So it's not A. It doesn't increase the current capacity. So that's not B. You don't want to couple the wire to other signals. That's D. So it's to prevent unwanted signals. C is the answer. Which of the following displays an electrical quantity as a numerical value? An electrical quantity as so potentiometer is a variable resistor. A transistor is a semiconductor. A relay is a powered switch. So it's got to be meter. Meter is how you display a numerical value. C. What type of circuit controls? What type of circuit controls the amount of voltage from a power supply? The answer is A. It's a regulator. It's not an oscillator. It's not a filter. It's not a phase inverter. What component changes 120 volts AC to a lower AC voltage for other uses? Well, it's not a variable capacitor. It's not a transistor. It's not a diode. So it's a transformer. B, transformer. Which of the following is commonly used as a visual indicator? Well, bipolar transistor is not a visual indicator. Neither is a Zener diode. Neither is a FET. So light emitting diode, or A, LED, is the answer. Which of the following is combined with an inductor to make a resonant circuit? So you've got an inductor and you've got a resonant circuit. It's not a resistor. It's not a Zener diode. It's not a potentiometer. It's a capacitor. So remember, resonant circuit is a capacitor and an inductor at the right frequency. What is the name of the device that combines several semiconductors in one package? That's not a transducer. It's not a multipole relay. It's not a transformer. It's an integrated circuit. C. Which of the following is resonant or tuned circuit? An inductor and capacitor in series or parallel, a linear voltage regulator, a resistor circuit used for reducing standing wave ratio, and a circuit designed to provide high fidelity audio. Well, we talked about resonance. That's kind of the basic function, and you'll see resonant circuits a lot. So an inductor and a capacitor in series or parallel is a resonant circuit. And that's it.
What I wanted to point out, Michael, was the questions in the question pool have the answers in a a specific sequence. They may not be in the same sequence on your actual exam. So do not look at a question and say, oh, the answer to this is A. You need to know not the letter of the answer, but the correct response. The order of the answers can be jumbled up. In the question pool book, it might say the correct answer is A. On your exam, it might be D. So that's just something to look out for.
And I'll also point out that when you're taking the test, if there are 4 or 5 people in the room taking the test, they could all have completely different sets of questions. So your questions and their questions might be completely different.
That is absolutely the case. And when we get to a good point here, one of the things I skipped over was the actual testing procedure. I talked about there being 35 multiple choice questions, but didn't go into the details about the upcoming test sessions and where you'll be able to take an exam once you've completed the course.
So I just want to, in the email that came around to give everybody the Zoom contacts, it's got my contact information. If you have questions about anything I talked about or anything that comes up in the class, feel free to send me an email, and if we need to, we'll set a time to talk on the phone, or I'll send you some resources or whatever you need. I'm happy to help get through this, because I know it's a lot to learn all at once. But lots of people do it, and lots of people that aren't electrical engineers do it. So I'm sure we can get through it if we work at it.
I just want to say, I went through this course the last time I put it on, which was like 1.5 years ago. I've been licensed about 1.5 years. And if your head isn't spinning, you're ahead of the game, because after this first one, my head was kind of spinning. So don't feel like you're overwhelmed. Don't bail out on us. It'll all come together for you. Just take a look at the material they gave you. Go over it. Look at the book. It'll all come together. You don't have to get every single question right. Remember, you only have to get 26 of the 35 they give you. So just relax. It'll come to you. Just take a look at the stuff and relax. That's all.
Yeah, and I can't overemphasize that hamstudy.org application is fabulous for practicing. And the advantage is that you see the same questions put in different ways, but it randomly brings up questions, especially the ones that you didn't get right last time. So it's a great way to practice, so that when you go there for the test, you've seen all these questions. You've seen them bunches of times and you know what the answers are. So it'll make things much easier. So I really, really recommend that app, the hamstudy.org app.
All right. Why don't I mention just a little bit about the testing? Your exam will be conducted by volunteer examiners. Used to be the FCC ran the show. Now they've turned it over to other hams. There is a session scheduled in Ukiah on April 15th, Saturday, April 15th, at the Redwood Academy. Show up at 9:30. There is a $15 fee for taking the exam. So be aware of that. Please bring cash. If you are under 18 or under, that fee will be discounted to $5. In addition, once you pass the test, the FCC has recently initiated a $35 fee to actually issue the license. The license is good for 10 years, so it works out to $350 a year. $3.50 a year. So it's still a bargain. I come from old school where they didn't used to charge you for that, but just so you got a heads up on that. And the information that you provided to enroll in the course can be transferred to the test session signups, and all we'll need at that point, if you haven't done so already, is to get a federal registration number or an FRN. But more details on that. But that's how the testing will go. I'll back out and see if there's anything else. Oh, yes, Fort Bragg. Yes, there will be test sessions in Fort Bragg. Mike, you want to give the details on that?
Yeah, we had enough requests for a Sunday session because people couldn't, they either had to work or they had other commitments on Saturdays. So we've scheduled a Saturday session and a Sunday session. We're hoping that we have everybody come to one or the other so we don't have to do both, but we are scheduled for two separate sessions. You have to sign up in advance so we know who's coming because we need to have the right materials. But the test session will be at noon at the Fort Bragg Senior Center. And I think the address is on the website, but if you'll probably be contacted by the guy who's organizing the test session to see if we can decide on just Saturday or just Sunday. But if not, we're going to do both. So we want to get as many people licensed as we can. So right now we're scheduled for a test session on Saturday and a test session on Sunday. Some people are asking, do they have to come to both? No, you only have to come to one. But we need to know your preference so that we can make sure we have enough materials at each session. And again, that's Fort Bragg Senior Center in Fort Bragg.
And that is on Saturday, the 7th or Sunday, the 8th of April, correct?
That's right. And you have to go to the McArk's website. I think it's, let's see, McArk's website under the news heading. And there's a link to sign up. You have to have signed up ahead of time or we won't have the information you need to actually take the test. So you have to have signed up for the test session in advance and get your FRN number and then show up that day.
Okay, just talking, looking forward to next week. I'll be covering the two sections next week. The study notes for that and the presentation should be posted in the Google Classroom ahead of the session. So if you want to get a sneak peek at that, you can have a look. And as far as whether we're going to do in-person sessions next week, a lot of it depends on the weather and the level of interest. But I will be, if there is enough interest, I would be in Ukiah for next week's presentations, and those will be are scheduled to be conducted at Public Health on South Dora. But we'll figure out that here hopefully sooner than later. Hopefully this abnormally winterish weather will go away.
One more thing, please. Someone in the chat did mention that the actual dates for the Fort Bragg test are the 8th, Saturday the 8th, and Sunday the 9th of April.
Yeah, that's right. At noon. And the address of the Fort Bragg Senior Center, if you don't know, is 490 Harold Street.